Hello and welcome. My name is Mohit Kumar Jangid, and it is my honor to present our work in this conference. Together with Professor Guoxing Chen and my both advisor, Professor Yinqian Zhang and Professor Zhiqiang, we made a first attempt towards formal verification of state continuity for enclave programs. Let's start with the necessary background information to understand the problem. If we look at the commodity operating system, it protects user data by process isolation and access control. And this comes with an assumption that operating system is trusted. But what happens when the operating system gets compromised? That's where the Intel SGX comes in. It is a trusted hardware solution to protect confidentiality and integrity of runtime code and data. In this ecosystem, application is divided into trusted and untrusted code section. The trusted code part, which is hardware encrypted, runs inside the protected memory regions called Enclave. And thus, if an adversary gets access to the operating system, she cannot observe the runtime data in plain text. Another concept involved in our paper is state continuity. And it is classically defined as a property of protected modules. And it requires that protected module must resume from the same execution state after TCP interrupts. Here, TCP implies trusted computing base. In the context of Intel SGX, the definition involves new players. The one of these is heterogeneous TCP modules. For example, we have enclave memory with local and global variables. We have non-volatile memory, such as monotonic counter, and persistent storage, such as sealed data. We also have a new threat model, where the adversary controls the privilege code. She can arbitrarily instantiate thread and processes. She can permute reorder enclave calls, and she can access to eCall and OCall arguments. Therefore, we redefine state continuity for enclave program. Consider an enclave program with different eCalls coordinating with monotonic counter and sealed data. And we define state continuity here as for all enclave execution, they always execute on the expected TCP state under SGX Threat Model and TCP interrupts. Let's understand this with an example. Consider the SGX application Sawtooth. It is a permissioned blockchain framework where different applications can utilize it to build customized blockchain application. One of the consensus algorithm involved in this framework is proof of elapsed time, which leverages Intel SGX for fair node participation. Each node in this workflow starts with registering into the blockchain network and then participates into block leader election. The election is split into two enclave calls. In the first eCall, it first generates random wait duration, which serves as the elapsed time in proof of work. Then it creates a reference monotonic counter value, and then it seals these two values and waits outside the enclave call for the elapsed time. The second eCall unseals the sealed data from the first eCall, and then it verifies the elapsed time. It also compares the recent monotonic counter value with the reference monotonic counter value. And then if all checks passes, it generates the proof of elapsed time certificate. And a node in a leader election can cheat by generating multiple certificates and gain the favor of elapsed time. Therefore, the equal2 also increments the monotonic counter in the end so that the later execution of equal2 cannot generate duplicate certificates. Overall, Sawtooth expects its TCP stage to remain either in a pre-certificate generation state or generate the certificate when the monotonic counter value equals the reference value or abort in all other states. And an adversary can influence the state continuity by replaying the sealed data or reordering eCalls or interleaving the enclave call operations. And there could be many other attack vectors. And therefore, we think that the state continuity is an important property to prove. In our investigation, we found that out of 196 SGX applications, 59 of them using ceiling API, 15 using monotonic counter API, and 5 using global variables. So the research problem we pose is that state continuity properties are difficult to verify in SGX environment. And it is because of the tedious and error-prone manual efforts involved. Here, one must clearly understand the trusted and untrusted boundaries, correctly coordinate among heterogeneous TCP modules, and carefully apply synchronization and lock. And so the question we pose is there a systematic approach to verify state continuity? And to this end, we propose to use symbolic verification tool. In its very basic flow, Tamarin Prover starts with the design logic of a protocol in the form of multi-set rewriting rules and the security property in the form of first order logic. And then it outputs whether the property holds for all execution of the model. And our key observation is that the cryptographic protocol share common features with SGX environment. The agents in the protocol can be considered as e-calls in the SGX side, and the adversary on public channel can be considered as adversary in the privilege code. We also note that the Tamarin input language is dynamic enough to customize the SGX environment. So overall, we start with the enclave execution logic and SGX threat logic derived from a component of an SGX application, and we systematically transform it into Tamarin input language. And then we verify state continuity property for all execution of the model. In our contribution of the systematic transformation, we derive many SGX primitive and we provide model templates for 3 open source SGX applications. The example of SGX primitive include enclave threads, association network of SGX entities, monotonic counter, etc. Example of programming primitive includes logs, loops, and branching, etc. We also carefully model each capability of SGX threat adversary. And these capabilities acts in compatibility with all the way we model SGX primitives. So let's look at how we build Tamarin model for the Sawtooth case. Recall that in Sawtooth, each node executes in 3 steps. And the election round is split into 2 enclave calls. And overall, there are many components required to model the workflow. Let's start with the SGX entities. In a blockchain network, each node executes in 3 steps and a user acts at each node. And these nodes interact with the blockchain interface. And this network can be considered as one network deployed by a developer or an ISV termed in the context of Intel SGX. And there can be multiple ISVs with different blockchains, and each node can have multiple processes executing those 3 steps. And so let's see how we build the association network of these entities. We utilize different properties of Tamarin input language objects. One of these is fresh facts, which can produce unique variables. A Tamarin rule which contains these facts can be instantiated unbounded number of times. And we utilize these 2 properties to produce different instances of ISVs. And we pass down the ISV entity variables to the second rule where we instantiate user and node instances, and which starts to form a hierarchy of ISVs, users, and node. And following such procedure for the process level, we create a 3-level hierarchy of ISVs, user nodes, and processes. Let's look at how we configure enclave threads. We utilize 2 types of facts in Tamarin. Linear facts can be consumed only once. So we use it to bind different rules of one enclave thread unit. And the other type of fact is a persistent fact, which can be consumed unbounded number of times. And we utilize the linear fact dependencies starting from the association network to configure a single thread, and we utilize the persistent fact dependencies from the association network to configure multiple threads. And in this manner, we model all other components of the Sawtooth workflow. Let's recall the state continuity property. We required that each node must not generate two certificates with same monotonic counter reference value. In its first order logic query, it is encoded with the help of timestamps, where two proof of elapsed time certificate execution events with the same node and same monotonic counter should correspond to one timestamp. Once the model and the state continuity property is ready, we feed it into the Tamarin Prover, and in its raw form, we derive an attack. Tamarin Prover shows a detailed trace of the Sawtooth workflow to show the root cause of the attack. And we apply a patch in the form of slight change in the logic, and we also derive a model where the state continuity property holds. Overall, we apply our methodology to 3 open source SGX applications, and we build safe and vulnerable model for each 3 cases. To conclude, our work is first attempt towards symbolic verification tool to verify state continuity property for SGX Enclave program. We demonstrate our approach using 3 open source SGX applications, and we show that Tamarin Prover can effectively model SGX-specific semantics and state continuity properties. Our Tamarin code is released at GitHub at the provided URL. I hope you enjoyed our talk, and I would like to thank you for your attention.